Hello and welcome to today's session. In today's session, I am going to make you familiar with support vector machines. A support vector machine is a powerful machine learning algorithm widely used for both linear and non-linear classification as well as regression and outlier detection tasks. SVMs are highly adaptable, making them suitable for various applications such as text classification, image classification, spam detection, handwriting identification, face detection, and anomaly detection. SVMs are particularly effective because they focus on finding the maximum separating hyperplane between the different classes in the target feature, making them robust for both binary and multi-class classification. In this outline, we will explore the support vector machine algorithm, its applications, and how it effectively handles both linear and non-linear classification, as well as regression and outlier detection tasks. Support vector machine. A support vector machine is a supervised machine learning algorithm used for both classification and regression tasks. While it can be applied to regression problems, SVM is best suited for classification tasks. The primary object of the SVM algorithm is to identify the optimal hyperplane in an n-dimensional space that can effectively separate data points into different classes in the feature space. The algorithm ensures that the margin between the closest points of different classes, known as support vectors, is maximized. The dimension of the hyperplane depends on the number of features. For instance, if there are two input features, the hyperplane is simply a line, and if there are three input features, the hyperplane becomes a 2D plane. As the number of features increases beyond 3, the complexity of visualizing the hyperplane also increases. Support vector machine terminology. First is hyperplane. The hyperplane is the decision boundary used to separate data points of different classes in a feature space. For linear classification, this is a linear equation represented as wx plus b equal to 0. The second terminology is support vectors. Support vectors are the closest data points to the hyperplane. These points are critical in determining the hyperplane and the margin in support vector machine. Margin. Third terminology is margin. The margin refers to the distance between the support vector and the hyperplane. The primary goal of the SVM algorithm is to maximize this margin, as a wider margin typically results in better classification performance. Kernel. The kernel is a mathematical function used in SVM to map input data into a higher dimensional feature space. This allows the SVM to find a hyperplane in cases where data points are not linearly separable in the original space. Common kernel functions include linear polynomial, radial basis function, and sigmoid. The next terminology is hard margin. A hard margin refers to the maximum margin hyperplane that perfectly separates the data points of different classes without any misclassifications. Next terminology is soft margin. When data contains outliers or is not perfectly separable, SVM uses the soft margin technique. This method introduces a slack variable for each data point to allow some misclassifications while balancing between maximizing the margin and minimizing violations. The C parameter in SVM is a regularization term that balances margin maximization and the penalty for misclassifications. A higher C value imposes a stricter penalty for margin violations, leading to a smaller margin but fewer misclassifications. Dual problem. Dual problem is the next terminology. The dual problem in SVM involves solving the language multipliers associated with the support vectors. This formulation allows for the use of the kernel trick and facilitates more efficient computation. Now, let me demonstrate a particular Python program in which I have implemented support vector machine. So, firstly, let me execute this Python program. Now, let me break this Python program into parts and explain you accordingly. First is import libraries. Datasets used to load built-in datasets like the Iris dataset. Train underscore test underscore split splits data into training and testing sets. SVC The class for support vector machine where you specify the type of kernel, example linear, polynomial, radial basis function, classification underscore report, and accuracy underscore score used to evaluate the model's performance. Second is loading the Iris dataset, iris.data. The feature set attributes like sepal length, petal width, iris.target. The target labels the species of the iris plant, train/test split. The data is divided into 80% training data and 20% test data. Create and train SVM. The SVC class is initialized with a linear kernel. The model is then trained using fit method on the training data. Prediction and evaluation. The model predicts the class labels on the test set, predict function or predict method. Accuracy and classification report are used to evaluate the model. The classification report includes precision, recall and F1 score for each class. So now let me also explain the output. First is accuracy. This tells us how many of the predictions were correct. In this case the accuracy is 100%. Second point is classification report. This gives a detailed performance measure for each class. First one is precision, the proportion of positive results that were actually correct. Second one is recall, the proportion of actual positives that were correctly identified. Third one is F1 score, the weighted average of precision and recall. The next point is types of support vector machine. Based on the nature of the decision boundary, support vector machines can be divided into two main parts. Linear SVM. Linear SVMs use a linear decision boundary to separate the data points of different classes. When the data can be precisely linearly separated, linear SVMs are very suitable. This means that a single straight line in 2D or a hyperplane in higher dimension can entirely divide the data points into their respective classes. A hyperplane that maximizes the margin between the classes is the decision boundary. Non-linear SVM. Non-linear SVM can be used to classify data when it cannot be separated into two classes by a straight line. In the case of 2D, by using kernel functions, non-linear SVMs can handle non-linearly separable data. The original input data is transformed by these kernel functions into a higher dimensional feature space where the data points can be linearly separated. A linear SVM is used to locate a non-linear decision boundary in this modified space. Advantages of support vector machine. First is high dimensional performance. SVM excels in high dimensional spaces, making it suitable for image classification and generation expression analysis. Non-linear capability. Utilizing kernel functions like RBF and polynomial, SVM effectively handles non-linear relationships. Outlier resilience. The soft margin feature allows SVM to ignore outliers, enhancing robustness in spam detection and anomaly detection. Binary and multi-class support. SVM is effective for both binary classification and multi-class classification, suitable for applications in text classification. Memory efficiency. SVM focuses on support vectors, making it memory efficient compared to other algorithms. Disadvantages of support vector machine. Slow training. SVM can be slow for large data sets, affecting performance in SVM in data mining tasks. Parameter tuning difficulty. Selecting the right kernel and adjusting parameters like C requires careful tuning, impacting SVM algorithms. Noise sensitivity. SVM struggles with noisy data sets and overlapping classes, limiting effectiveness in real-world scenarios. Limited interpretability. The complexity of the hyperplane in higher dimensions makes SVM less interpretable than other models. Feature scaling sensitivity. Proper feature scaling is essential, otherwise SVM models may perform poorly. That's all for today. Thank you for listening me patiently. Let's meet during the next video or during the next session.